Hi everyone, in this video we're going to introduce chi-squared distribution, and specifically we're going to start with a more simplified version. And this one is not as common on the AP, but it does show up, and it's called the chi-square test for goodness of fit. So let's pretend like the M&M company advertised the distribution of the color breakdown of their colors. And let's say that they're claiming that 12.5% of their M&Ms are the color brown, and 12.5% are green, red, orange, etc., etc. So they have the distribution here down below. These numbers are considered population numbers, population parameters specifically, because they're talking about their population. So this is the P sub brown, this is the P sub green. Notice I'm using the symbol P without a hat. This is P sub orange, P sub yellow, and P sub blue. And notice they're claiming that these are overall, the percent of orange is 25% in the population of all M&Ms created. So the population of interest is all M&Ms produced by the M&M and Mars company. And the parameters are all of these color breakdowns, and we would list them all if we wanted to. So now I take a sample. I take a random sample of 60 M&Ms, and that is called N. And I open up my bag, I get 60 total M&Ms, and I count how many I get of each color. And these numbers are denoted here. These numbers are what I actually got. So I'm going to use the word actual or observed here, okay? So I actually got 12 brown, 3 red, 7 yellow, etc., etc. All right, and that totals up to 60. So the question with the chi-squared is, are the numbers that I got actually in my bag consistent with the advertised percents, or are they different? Are they off? Is at least one of the percent breakdown different from the advertised, okay? So because there's more than one proportion, there's actually more than two proportions. Instead of calling this a 1 proportion Z test or a 2 proportion Z test, there's too many proportions here. There's 1, 2, 3, 4, 5, 6 proportions. So this now becomes too hard to do a 2 proportion Z test because there's 6 of them. So there's a lot going on here at play. So we do a chi-square test instead, a chi-square test specifically for goodness of fit, meaning how good is the fit of my actual M&Ms to what was advertised. So in symbols, my null hypothesis would be the P brown equals 0.125, which is what they advertised. The P green is 0.125, which we advertised. The red is what they advertised. The orange is what they advertise, etc. Instead of listing this all out, which is what I'm doing essentially, I could write in words all proportions of colors, breakdowns, the breakdown of colors are what is advertised or claimed by the company. And then the alternative hypothesis would basically be at least one of these is different than what's advertised, because if at least one of them is off, that's going to throw the breakdown of at least another one, and it's not going to be what's advertised. So in words, I could just say at least one of the proportions is not what is advertised by the company. Okay, so basically that means that the whole breakdown of colors is not what the company really advertised. So now what we have to do is we have to find and calculate the expected values that would have been if indeed the breakdown was what was advertised, because there are 60 M&Ms in our bag, 60, that's N, and we want to know if they were what was expected, what would they have been? And then we want to compare what we actually got to what was expected and see how off it essentially was. So in order to do that and to find the expected values here, what you want to do is multiply the sample size N by the advertised percent for each color. or whatever it is that we're talking about in the question. In this case, we're talking about color. So for example, they have brown here. They have the total in the sample is N, 60, and then the advertised percent for brown up top was 12.5%. So you guys know, remember back in the day, if you guys look down below into the box here, remember expected value for a binomial setting. The expected value for a binomial setting was N times P, or the mean, what's expected, was N times P, where N is the total amount and P was the probability of success. So here they're taking the 60 total and they're multiplying by the advertised percent for brown, and they got 0.125 times 60 was 7.5. So we can expect, we should have about 7.5 browns in our bag, okay? So now if we look back at what we got, we did not get 7.5 browns in our bag. I'm going to highlight it. We got 12 rounds in our bag. So how off is the 12 from the 7.5, which is what is predicted? So how off is the actual from what's predicted? It kind of sounds like a residual, which we did back in the regression chapter. It's just now we're talking about a categorical variable because it's categories of colors. So what I want you to do now is I'm going to pause the video and I want you to do this for every color. Calculate the expected value for every color. So take the N, which is 60, and multiply it by the advertised percent or proportion from above and write down the expected counts for every color. So I got my expected counts for brown, red, orange, yellow, blue, and green, and they're listed up top here. I have 7.5, 7.5, 15, 7.5, 15, and 7.5. So if I were to add all of those together, I should get the expected total, which is 60. 7.5 plus 7.5 plus 15 plus 7.5 plus 15 plus 7.5. This should equal the total in the sample, which is 60. What did I do wrong? Oh no. All right, I got to insert a plus sign here. Sorry. All right, so once we have that, that's great. Now we have our expected counts. So if you look down below here, you see that what they did was display this in the form of a handy table. You could make your table going up and down like this, or you could make your table going across and make it into rows. So you see that this is what actually happened, and this is what expected to happen. Another name is observed and expected, or actual and predicted. So the expected counts are the ones that we just calculated when we multiplied the N times the P that was advertised. And then the observed or actual count is what I actually got in my bag when I did just open my bag and see what I got. Okay, so these should both total to 60. So now you see that it is displayed in the form of a bar graph, because remember it's categorical data and categorical data is displayed by a bar graph. So what we're trying to figure out is how off is what actually happened from what was expected to happen. So from the bar graph you can see that some colors are more predictable, like yellow seemed like what actually happened was what was predicted to happen, but something like blue, it seemed like what actually happened was we got a greater percent of blue than what was predicted. Okay, so we want to know how statistically significant this is. Is it significantly different, the observed counts from the expected, and the breakdown that they were predicting, is it totally off, or is it consistent with what they averaged? So before we move on, what we're going to do is we're going to enter our data in our list. We're going to clear our list, and then we're going to press Stat Edit, and in L1 we're going to enter the observed data, and in L2 we're going to enter the expected data. So the observed data is what actually happened. So we're going to enter 12, 3, 7, 9, 9, and 20. And then the expected is what we predicted was going to happen. So those are going to be more similar to each other because they were all the same percents, 12.5, 12.5%. 15, 15. Okay, so once we have that, we're going to move on here. So now it says, basically, we are going to calculate what's called the chi-squared test statistic for each cell. So for each color, we're going to find out how off is what actually happened from what was predicted to happen. And that is going to be this chi-squared test statistic. The formula for the chi-squared test statistic is on the reference sheet, so I want you to write that down. Formula sheet. I'm going to show you where it's located, but let me explain what it is. Chi squared is denoted with the letter x, so that's the x squared. And we have that symbol summation again, and that means sum. So remember, this number means sum, which means add them all up. So what you do is you take the observed amount, which is what actually happened, and you subtract the expected. Actual minus predicted. Doesn't that sound familiar? That's actually the residual formula. So you want to take what actually happened and subtract what was predicted to happen. And then we're going to square them because some are going to be positive, some are going to be negative. We're going to square them to get rid of the negative. So it's going to basically just become a distance away from what was expected and divide by expected to get a ratio. So observed minus expected squared over expected. That would be the one cell that we would do. And then we're going to add it all up for every single color. And that sum is going to be the total chi-squared test statistic for the entire problem. So if you look at example, the colors here that we had on the previous page. Okay, observed minus expected squared over expected. I'm going to highlight the first one, which was the color brown. Remember how back when we did expected value, you don't really have to write out every single um, term. You can write out the first term and then a little dot, 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 and then the last term with a plus sign in between, indicating that you know that addition is happening. So the first one was brown, so I'm going to do brown. Observed was 12. 12 minus expected, 7.5, squared over expected, 7.5. So that would be the brown one, okay? So I'm going to write brown under that. And then I'm going to put a plus sign, a dot, 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 another plus sign, and I'm going to skip over to the last term, which was blue. The observed blue was 20. The expected blue was 15, squared over expected, 15. I'm going to write blue. So basically, I would do this for all 6 colors, and I would add them all up, and I would get the chi-squared test statistic for the total distribution, okay? So that's what I'm going to show you they did over here on this page. So looking down below, you see they did the same thing as me. They did brown, they did a dot, 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 they did blue, they calculated all of them, they added them all up, and they're going to get their result, okay? Now I'm going to show you where to find it on the formula sheet. Okay, so on the formula sheet, if you're looking at this symbol that says 3 inference and you go down here, you're going to see that we have underneath the confidence interval and the test statistic, here it is, chi-squared test statistic. Observed minus expected squared over expected, or actual minus predicted squared over predicted, and then you add them all up. So there you go, there you have it. So now they're showing you if you had simulated this sampling distribution, if you had done this many times, and they said 1,000 times of samples of the same size 60, they would get this picture here. And notice the shape. What is this shape? Excuse me. I'm hoping you're saying it's skewed to the right because the tail is on the right. And it is skewed right, and it's always going to be skewed right, and it's always going to be skewed right because since everything is squared, you're going to get rid of the negatives, and there's never going to be negative test statistics, so it's always going to be positive, okay? So basically what we want to know is if we do our chi-square test statistic, okay, if the actual is equal to the predicted and it's spot on, like they're predicting that you're going to get 7.5 brown, and indeed you get 7.5 brown, then if you did 7.5 minus 7.5 squared over 7.5, you're going to get 0 because the actual would equal the predicted. If the actual equals the predicted, the chi-squared will be 0 or close to 0 if it's very close. The bigger the difference between the actual and the predicted, the bigger the chi-squared value is going to be. And the bigger that total chi-square value is going to be, the further away it's going to be away from 0. So let's say it's to the right, and they got this chi-square test statistic here of 9.8 from above. 9.8 is showing that there is a difference between the observed and the expected. The further it is to the right, the more the observed differ from the expected, because remember, we're measuring the observed minus the expected to see if the observed actually equal the expected, okay? So the further it is that the observed is away from the expected, the further the chi-squared value is going to be to the right, and the more it is to the right, the lower the p-value. And the lower the p-value, the more likely you are to reject the null and rule in favor of the HA. Okay, so when we do this, we're going to put it in the calculator, but we have to note that we're going to need the degrees of freedom. For this, the degrees of freedom is a little different. You have to take the number of categories, so in this case, it was the number of colors, and subtract 1. So there were 6 total colors for the M&Ms, so we're going to do 6 minus 1, and we're going to get 5 degrees of freedom for this question. Okay, and then the p-value is going to be the probability of getting a chi-square value, a test statistic value, as large or larger than whatever we get for our chi-squared value, assuming that the null hypothesis is true. Okay, so I want to skip over to the calculator, and we're going to do the calculator method first. Okay, so notice we already did this. We put the observed counts in L1, we put the expected counts in L2, observed, expected. Then we're going to go to the chi-squared test, goodness of fit. Specifically, GOF is goodness of fit. So let's do that together now. To get there, we press stat, we go over to test, and we're going to go down or up. I say up, maybe easier, and choose letter D for dog, chi-squared test for goodness of fit. Choose it. Now, where are your observed counts? They're in L1, so you're going to press second 1. Where are your expected counts? They're in L2, so you're going to press second 2. And then the degrees of freedom is 6 minus 1, which is 5. We could choose calculate or draw. If we choose calculate, we'll get the same chi-squared test statistic, which is 9.8, and we'll get our p-value. And also on the bottom, it says CNTRB. These are the chi-squared test statistics for each individual color. So basically broken down by color, brown, orange, yellow, whatever, all the way to blue, that would have been each chi-squared cell. All right, if we choose draw, let's do it again and choose draw. Again, it's letter D, chi-squared test for goodness of fit. If we go down to draw, we're going to see that the chi-squared test statistic is skewed to the right. Sorry, let me get rid of whatever's in here the plot was on. I'll do it again. And skewed right, again, is always going to be the case. All right, it's also going to tell you your p-value on the bottom, and it's going to tell you your test statistic, which is your chi-squared value. So basically, we are doing phantoms with a test statistic, and the test statistic is the chi-square, which is the 9.8. And that is what we got when we did it by hand back on the last slide. So notice the p-value is 0.081, and is 0.081 less than 0.05? I'm hoping you're saying no, it is not. So if I go back to my null hypothesis, I would not have rejected the null hypothesis because the p-value was 0.081, which is not less than 0.05. I fail to reject the null hypothesis. Thus, I cannot conclude the HA, which says at least one of the proportions is different than advertised. So this is kind of substantiating that maybe their advertisement is kind of correct and the proportion breakdown of colors is actually what they're claiming that it is. The last thing I want to mention, if you find this slide again, is how to use the chi-squared table for this. We did go over how to use the calculator, and I always prefer the calculator, but there is also a chi-squared table. And that chi-square table is called table C. So I want to show you guys that now. If you go down to table C, go past A, go past B, and look for the one that looks skewed right here it is, chi-squared. And then basically what you would do is you would go to the degrees of freedom, which was 6 minus 1, which is 5. And you would go across this row and you would find your chi-square test statistic. If you go back to the question, we got a chi-square test statistic of 9.8. 9.8 is between the numbers 9.24 and 11.07. So if we had gone up with our eyes to the top, this would correspond to a tail probability between 0.05 and 0.10. And indeed, that's what we got. We got 0.08 for our p-value. So notice it is within the range 0.05 to 0.10. So this is what this is showing you here. 9.8 is between these two values, and that corresponds with the p-value between 0.05 and 0.10. So that's what I'm going to write here. It was between 0.05 and 0.10, so it was not statistically significant at the alpha equals 0.05 level. The last thing that I want to talk about is the conditions that we're supposed to check. When we're doing phantoms, remember that we get to the A step, which is assumptions or conditions. We still have to check if the sample is random. Is it an SRS taken from the population of interest? Is 10N less than the population of interest. And the last one, basically this is the only different one, so I'm going to star it, is that all the expected counts have to be greater than 5. They also have to be greater than 1, but really they have to be greater than 5, okay? So the bigger the sample size, the more all the expected counts would be greater than 5. So if we do go back to our original data, all the expected counts were greater than 5, which you see here. This column here, they're all greater than 5, so that's good to go. And that's because our sample of size 60 was large enough. So I just want to remind you, we would put all of this together in the form of phantoms. We would do our population of interest, our hypotheses, we would do all of our assumptions. The name of the test would be called the chi-squared test for goodness of fit. And then we would proceed showing our formula for our test statistic, which is right here, test statistic. Then we would show the number plug-in of at least the first term, a dot, 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 and then the last term. And then we could go to the calculator to get our test statistic value, which is 9.8. And we could go to the calculator to get our p-value. And then we make our decision and we make our conclusion. So it's really following along the same way and everything we've been doing so far. It's just a different way of looking at it because there's more than two proportions. Thank you.